record this also, right? Because, yeah. So this is the problem. The next question that I want to talk about, since you've already done trees, it's good to just think about a relation between trees and matchings, right? Whether a tree has a perfect matching, and what can we say? Trees and perfect matchings. So let's draw a tree and then talk, right? Let's draw a small tree. Obviously, I have to draw a tree with even number of vertices. Otherwise, it doesn't make any sense. Let's just make a few more. Okay. Let's draw. I'm drawing a tree like a tree. So always, when you're studying a new concept, try to tie it up with, just ask the question, the previous concept, because you already understand that thing familiarly. So it will help you to discover good things. So I'm just drawing it in a level diagram. So I'm not joining things on the same level. Yeah, this is a very silly, simple tree. Maybe I draw a richer tree somehow. Maybe. No, let's just leave it like this. Okay. Yeah, let's leave it like this for now. And so, yeah. So does this tree have a perfect matching? Does it have a perfect matching? Let's think. It should be very simple to say. Right. No, right? Why? Okay, why? Maybe I'll start. Mm-hmm. Okay, right. Mm-hmm. Yeah, so in some, so you're basically saying that something will remain unused, some vertex will remain unused. That's simple reason, right? So, okay, is that, does everybody see that, right? Because if you try to use up all the vertices, you see it's simply not possible. Okay, and there's a very simple thing, because these two leaves have the same option, right? These two leaves have only one option, that is this 2. That's a simple reason why it's not possible, right? Either a 5 or 6 will be unused. In any matching, either this 5 or 2 and 5 will be used, or 2 and 6 will be used. Both cannot be used, because in a matching, we know this. Unab, is this point okay with you? That in any matching, if I use 2 and 5, then I cannot use 2 and 6. I cannot use the edge 2, 6. Is it okay? Because then it won't be a matching, right? You cannot use the same vertex in 2 different places, as you know this. So then if you use 5, then you cannot use 6. So that's for this very simple reason. There's a very simple obstruction. You can just clear the thing, right? So the answer is no. The answer is no, and we have given maybe 2 different kinds of reasons, but you see, this reason that I'm giving, this is so simple that now you may start thinking, when does a tree have a perfect matching? This is a question that I have not thought about before. I have not seen it anywhere. You can just think and write about it. right? I'll not talk about this more because it's something you should just think first. Okay, I don't know the answer myself. It will be a good question to think. Mind, please do this. I can already sense something good in this. Okay, have a perfect matching, because you can see with a very simple obstruction. That's why these small things, when you start thinking and writing, is how you will eventually think some original thing. Someone would have thought about this, obviously, but yeah, slowly. Okay, but this is not what I'm interested in. Okay, I will give you. Let me give an example of a. Oh no, yeah, I think it's so simple. It is so simple in the sense that the structure is going to be so simple that. Do you guys sense what kind of tree will have a perfect matching? Just general. Can you just give me an example of a tree with a perfect matching? A path? Anything other than a path? Obviously, an even length path with a perfect matching. Can you give anything other than a path? Let's try. So something other than a path would mean that I should do something like this, right? To begin with. I mean, there are other ways, but then if we say I will use this with this because I want to make an example, right? Then I have to use. So yeah, something other than a path does exist. I think this, and I'm just making example with everyone. I'm not thought about this before. It's a very simple thing to make. I mean, try to make more examples. You will kind of get when a tree has a perfect matching. But again, that's for late. That's for you to think in private first. Okay. So I have given a tree, and I have also given a perfect matching. Well, obviously the perfect matching kind of came first, but so at least we do have something to talk about. We do have a tree with a perfect matching. Everybody fine with this till now? This is a tree with a perfect matching. Now the question is, can you find another perfect matching? Just think. Yes, oh, yeah, in the same tree. Yeah. Can you find another perfect matching in the same tree? Oh, 1 second. I'll just wait. Is it happening here? Or? No, I think it's not some marriage. Yeah. Can you find another perfect matching in the same tree? I kind of barely made the exam. Ah, good. Yeah. It seems no, right? Is everybody feeling that? What? Aha. Yes, it's because of the leaves. And then you can move up from there, right? Does everybody feel this? What happened to the others? Okay. Does everybody feel that they cannot really make another perfect matching? Because any perfect matching, you have to use this leaf and then you have to use this edge. And then you can kind of build up from there, right? So this leads us to another conjecture. This is how you make your theory. And this is also a problem, but I kind of first wanted to do this and see how I could do it. Okay. I was thinking of something actually more complicated before. So if I would have not said it in this leisurely linear way, I would have tried to think of a more complicated proof and maybe would have failed. I was thinking about taking another perfect matching and then comparing them with the direct sum and some complicated thing. I would have got a proof by that also, but because there would be no cycles because the tree is so on and so on. But this is much simpler, right? Because of the leaves. Yeah. So now I'm just asking the question, prove that every tree has at most one perfect matching. And you can kind of see that. Okay. Prove that every tree. So it's the usefulness of example is for everyone. Okay. Beginner or more advanced or very, very advanced, whatever. Prove that every tree has at most one, has at most one. So in some sense, any graph which doesn't have cycle will have at most one perfect matching. Because the components you can take connected pieces and find the matchings there. It is the cycles that allow you to, kind of move around and find more perfect match. Once you find a perfect matching, it is the end of it. You cannot find more perfect matchings in this. Okay. Is everybody fine with this? And try to prove this. This is a theorem. This is the homework. Okay. So you can just basically an exercise in induction and a good understanding of matching. But you can do it in any way you want. So we have seen these things. Okay. Seeing these things. So we are getting some intuition about perfect matchings. And I will try to generalize these things to results, to theorems. The problem I gave earlier about friends, that certainly generalizes to maybe the most important theorem in matching theory used in this recent papers, recent things. Yeah, not very recent, maybe 20,000, 2000 something. And yeah, generalization of that, but the theory was. And then we are kind of also seeing that number of perfect matchings, if there exists one, this kind of depends on number of cycles. You can sense that, right? The more cycles you have, the cycles are the things that lead to more perfect matchings, even cycles. Or not odd cycles are kind of useless. If there is an odd cycle, you're kind of, no, you can still do, but point is, yeah, the number of cycles is there. This thing, right? And this kind of leads to a theory of, but this is beyond, we will not do this. Okay. But just saying for fun, this kind of leads to the theory of counting enumeration of perfect matching. That's a very big place. Okay. Enumeration of perfect matchings using cycles. So you kind of encode cycles in some sort of a matrix, and then some advanced stuff, and then you kind of take not a determinant, but you take something called a permanent. Okay. And there you kind of count cycles in permutations, the cycles of permutations, and so on. You count matchings in that, but that leaves a lot of work. Okay. Yeah, but this is just the small thing goes to that. But if you will not, yes, yeah, yeah, no, it's not close in the sense that they kind of move together. You see, in a graph, let's say if you have a perfect matching, okay, if you have a perfect matching, then if you have a cycle in that graph, right, that cycle in the graph will kind of allow you to make another perfect matching. Just think about it, right? And you can just take us, so locally, let's say there is a small cycle in your graph. Okay. And let's say this graph already has a perfect matching. Then the cycles is what you can use to create, to the symmetry of the cycle will help you to create more perfect matching. So for example, this is a small position in the graph, and the graph can have a lot of, but it's just locally we're looking at the graph here. I was going to think let's say, and whatever, right? But there is a perfect matching, okay? And let's say that in that perfect matching, this, because all the vertices are supposed to be saturated, then potentially these will be used, but it may not be some counter example, but you can kind of, a general picture, right? It is a big perfect matching and locally you're seeing this thing, right? Now, it could be, yeah, but you can see that exact saying the exact formula is very difficult, okay? I don't think there is, it sort of grows together in the sense of what, yeah, more cycles, more options, whether it's multiplicative or additive, I don't know, whether it's n factorial or n minus 1, I don't know, but it will grow. And that can be figured out maybe if in some conditions. But the point is you get this intuition. Like now, if you have this, then no one can stop you from instead taking these three. So you certainly get one more perfect matching. If there was a perfect matching uses the green, using the yellow ones, you can get another perfect matching using the green ones. Right. And this will also be a perfect matching, right? Because other edges, whatever they are, they will remain. Which are used, they will remain used. But here we are swapping these yellow ones with these green ones. And you get another perfect matching. So, and it kind of starts with the tree. The tree has no cycles. And a tree has only one perfect matching if it has one. Because there is no cycles to create a symmetry. So cycles do help you to create more perfect matching, but it seems like cycles are the only thing that helps you to create more perfect matchings, because when there are no cycles, you don't have more perfect matchings. That is the thing. So it's not just that when you have more cycles, you have more perfect matchings, but it's kind of cycles capture everything. So if you can put this theory or structure of cycles and put them in a good mathematical structure, then working with them will lead you to exact answers about perfect matchings. Because cycles seems to be the only thing, because when there are no cycles and there are no permutations of perfect matchings, there are no more perfect matchings. Okay, this is the thing, and these things that these are encoded in permanents and other things, and there are some, and this is a way like good thing, but I don't know the complexity theory side of it, but enumerated side of it I know a little bit. Okay, I mean, yeah. So first we do the basics, and later on you can. There are books of this, but little hard to read for now. Okay. So any questions for today? Okay then. So let's meet next time. I'll tell you. Okay. Thank you.